Hey everyone, welcome to this explainer. I'm really excited you're tuning in because today we're shining a massive spotlight on this hidden, honestly kind of silent, energy drain happening inside modern data centers all over the world. We hear a ton about cooling systems and throttling CPUs to save power, right? But there is this massive blind spot that constantly gets overlooked, and that blind spot is storage. So, let's dive right in with a pretty staggering statistic. 80%. Industry studies show that nearly 80% of all data stored globally is what we call write once, read never. We're talking about things like, your old Facebook photos from 2014, raw sensor logs from some IoT network, or just dusty compliance backups. It's this phenomenon known as the cold data crisis. This data literally just sits there, completely unused, taking up space.
And the sheer scale of this problem is honestly mind-blowing. Because traditional data centers keep thousands of mechanical hard drives spinning continuously at 7,200 RPM, basically just in case someone requests that forgotten cold data. The storage infrastructure itself can consume up to 40% of a modern data center's total operational power. 40%! That is a massive chunk of electricity just for data nobody is even looking at.
But hey, today we're going to fix that. Here is our roadmap to cure this power-draining crisis. We'll quickly cover the cold data crisis, dive into MAID architecture, explore the 4 levels of sleep, compare SSD, HDD, and tape, and then wrap the whole thing up with a comprehensive green IT strategy. You're going to walk away with a solid engineering blueprint. All right, let's get into Section 1, the cold data crisis, the hidden energy drain. So there's just a stark contrast between the old way of doing things and the new way. In a traditional RAID array, that's a redundant array of independent disks, 100% of those drives are frantically spinning 24/7. It is an absolute energy nightmare. But compare that to the zero-power silence of the MAID architecture, where up to 75% of the drives are fully stationary and just completely powered down at any given time. Which brings us to Section 2, MAID architecture explained, massive array of idle disks. So MAID stands for Massive Array of Idle Disks. It's a purpose-built, green alternative to RAID designed specifically for archival and cold storage. The core philosophy here is kind of brutal but absolutely brilliant. If a disk isn't actively being read from or written to, kill the power to it. Just turn it off. And the way it manages to do this without, completely destroying network latency is by using an intelligent MAID controller and a massive high-speed cache. Think of the controller as a really strict traffic cop. When a data request comes in, that controller checks the cache first. If the data is sitting right there, boom, it's served instantly. 0 physical disks need to spin up. But if it's not there, the controller wakes up only the specific idle drive that actually holds the requested data. Let's move on to Section 3, 4 levels of sleep. MAID power states. Now, to maximize the hardware lifespan and avoid these massive energy spikes when turning things on and off, MAID dynamically steps the drives through 4 distinct power states. Let's walk down this energy ladder together. We start up at level 0, the active state, where the drive is spinning at full RPM, read and write heads are flying around doing their thing. Then we drop down to level 1, unloaded. It's still spinning at full speed, but the heads are safely parked, which saves about 15 to 20% of power. Next is level 2, low speed. Here the platter actually slows down to a fraction of its normal RPM, saving up to 50%. And finally, we reach level 3, stopped. The spindle motor is completely powered off. The drive is effectively dead, completely silent until it's explicitly woken up. That saves a whopping 80 to 90% of power.
So the absolute crucial point, the big takeaway here, is this metric. By dynamically shifting petabytes of hard drives down into that level 3 sleep state, a MAID storage tier can slash a data center's cooling and power overhead by up to 75%. That is a massive, massive win for green computing.
All right, on to Section 4, SSD versus HDD versus tape, evaluating mediums. What we're looking at here is the ultimate green IT storage matrix. Because the true separators between inefficient storage and optimal green solutions are really the power to terabyte ratios and the latency metrics. We are evaluating solid-state drives, traditional hard disk drives, and magnetic tape based entirely on their active and idle watts per terabyte. Let's break this down.
First up, SSDs. Their green superpower is what we call the race to sleep. Because they utilize non-flash memory with 0 moving parts, an SSD can complete a task in literal microseconds and then instantly drop back into a low-power idle state. It basically finishes the job and powers down before a mechanical drive even has a chance to get up to speed.
On the flip side, traditional hard disk drives are honestly kind of a nightmare for energy proportional computing. Think about this. Even when sitting completely idle, doing absolutely nothing, an HDD still draws about 1.5 watts per terabyte. Why? Because it has to keep those heavy magnetic platters spinning at thousands of RPM just to overcome friction. It's wild.
But then, we get to magnetic tape, specifically linear tape open formats. Now, I know what you might be thinking. A lot of people think tape is this dead 1980s technology, right? But tech giants like Google, Amazon, Microsoft, they rely massively on automated tape libraries. Why on earth would they do that? 0.0 watts per terabyte when offline. Once data is written to a tape cartridge, it just sits on a shelf drawing zero power, none. Magnetic tape actually holds the title for the lowest operational carbon footprint of any storage medium in human history.
However, for sure there is a catch, and that catch is extreme latency. Tape is a fully offline medium, so to retrieve your data, an automated robotic arm physically has to fetch, thread, and spool that specific tape. That deliberate motion takes literal minutes, so it makes tape absolutely perfect for cold data, but completely useless if you need fast, instant access.
Which brings us to our final section, Section 5, the Green IT Strategy, the Action Plan. Okay, so let's put it all together. Here is the 4-step engineering synthesis that perfectly aligns your storage hardware with your actual data usage to maximize input/output per watt. Step 1, you've got to implement data classification. You have to separate the constantly accessed hot data from the unused cold data. Step 2, deploy SSDs specifically for that hot data so you can leverage their low latency and that awesome race to sleep capability. Step 3, for the intermediate or warm data, deploy the MAID architecture we just discussed. Keep 75% of those mechanical disks powered down in deep sleep states. And finally, Step 4, move all your absolute cold data over to magnetic tape, dropping that archival power draw entirely down to zero.
By doing all this, we've completely mitigated the power consumption of massive hardware data storage. It's a real game changer. But I want to leave you with a bit of a provocative thought here. We've optimized the storage hardware, sure, but what happens when we start cannibalizing the underutilized physical servers themselves to save megawatts of power? Just think about how virtualization and green software fit into this giant data center puzzle. The hunt for efficiency never really stops, does it? There is just so much more to uncover. Thank you so much for joining me on this explainer, and keep questioning how our digital world is built.